Hello friends, today I will discuss the numerical problem on circle diagram of three-phase induction motor. The data is given like this. A 4.5 kilowatts, 400 volts, 50 Hz three-phase delta connected induction motor give the following test results. No load test 400 volts, 4.2 amperes, 480 watts. Blocked rotor test 215 volts, 15 amperes, 1080 watts. The ratio of stator to rotor resistance referred to the stator is 1:2. Calculate the line current, power factor and efficiency at 125% of full load. To solve this problem, so there are totally four steps. First one is identify the unknown parameters. Second is analyze the known data. Third is draw the circle diagram. Fourth is find out the unknown parameters. First, let us identify the unknown parameters. So the unknown parameters here are line current and power factor and efficiency at 125% of full load. And from the unknown data, so we analyze like this. So before we analyze the given data, let us see what is the equivalent circuit of the three-phase induction motor when referred to the stator side. This is the equivalent circuit of three-phase induction motor per phase like this. This is the primary side, means stator side resistance R1. This is the primary winding per phase reactance, that is stator per phase winding impedance, the reactance is X1. And here there are no load components. So one is called the core loss component, which is in phase with the applied voltage, whereas this is the magnetizing component represented by a inductor like this, which draws the magnetizing current called IM. Resultant of this is nothing but the no load current, or the current when the rotor is, when it is rotating at free. So this is the secondary side or the rotor side components. This is the rotor reactance referred to the stator side per phase, and it is represented by X2 dash. And this is the resistance of the rotor referred to the stator side, that is R2 dash divided by S. This is the rotor current referred to the stator side represented by I2 dash. And this I2 dash we represent in this circle diagram with ISC like this. This is under blocked rotor condition, that is the current drawn by the rotor. And this is the no load components which we represent like this I naught, and this is nothing but the magnetizing current which lags the applied voltage by 90 degrees, and this is the core loss component which is in phase with the applied voltage called V. The resultant of this IM and IC is nothing but I naught, and the resultant of ISC and I naught is nothing but the net input current. This IM and IC is nothing but I naught. This I naught will lag the applied voltage by some angle. That angle we call as the no load power factor angle. So this we can replace with RL circuit like this, R1 L1. The effect of this on the applied voltage is again lagging, and this part is as it is, but we represent here L and R like this. From the circuit theory, we can draw the current locus diagram for this circuit like this. So we take the applied voltage on y-axis. When we calculate this I0 and we find that this I0 is lagging the applied voltage by some angle called phi naught like this. So this is nothing but current locus diagram of this circuit. And if you look at this, second branch is nothing but blocked rotor current, which varies with the resistance of the rotor circuit, but there is a fixed element called the inductance. When this R is equal to 0, and when the impedance of the circuit will become purely inductive in nature. In a pure inductor, when it is connected to the voltage, the current lags by 90 degrees like this. That we can show as a line which is parallel to the x-axis and perpendicular to the y-axis or voltage axis. Then, if we increase this resistance to infinity, the current will become 0, that is, it comes here. Whereas for the resistances which is more than 0 but less than infinity, we get the different points on this curve like this. So for this there is some short circuit current or rotor current, and for this some other current, for some other resistance, this is the current. Like this it will vary. So the circle diagram for the three-phase induction motor basis is only circuit theory. So that is, from the equivalent circuit of the three-phase induction motor, we get this locus diagram, and we use this locus diagram for drawing the circle diagram of the three-phase induction motor. So from no load test given data, we know that I0 is 4.2 amperes, and we know no load power is given by W0, and we can represent that as root 3 V0 I0 cos phi naught. So from that, we can calculate what is cos phi naught. So that is, we get 480 divided by root 3 into 400 into 4.2. Then we get 0.1649 lagging. So from this, when you take the cos inverse for this, then we get phi naught as 80.5 degrees. So means this phi naught will become 80.5 degrees. So from the short circuit test, we have the data. ISC is 15 amperes and VSC is 215 volts. WSC is 1080 watts. And we know WSC is nothing but root 3 VSC ISC cos phi SC. So from this we can write cos phi SC is nothing but WSC divided by root 3 VSC ISC, and WSC is already given, so that is 1080 divided by root 3 into VSC is already given in the data, that is 215 volts, and ISC is also known, that is 15 amperes. So once we simplify this, we get 0.1933 lagging, and from this when you take the cos inverse of this, then we get the phi SC is equal to 78.85 degrees. As motor is delta connected, per phase current is 1 by root 3 times line current. So we have to calculate per phase current. This ISC which is given is nothing but line current, that we have to convert into phase current, and that phase current we have to convert or calculate for normal voltage application under blocked rotor condition, that we represent with ISN like this. And we know ISC is for VSC. For a delta connected system, phase voltage and line voltage are one in this one. But ISC is given here as line current, so we have to convert that into phase current, that is 15 by root 3 is the phase current. For this phase current, the applied voltage is 215 volts. And the normal voltage or rated voltage of the motor is 400 volts. If we apply the 400 volts, what is the short circuit current under normal voltage application? So which is represented by ISN. So using this formula and substituting the values, then we get here 16.1121 amperes. And this is necessary to draw the circle diagram. Similarly, we need the corresponding copper the rotor block power loss, which is given by WSN, and it is also can be calculated using this formula, WSC into ISN square by ISC square. So we know what is ISN per phase, so that is 16.1121 amperes, and we know what is ISC per phase value, that is 15 by root 3. So we know copper loss is directly proportional to the current flowing square. So we write like this, 1080 into 16.1121 whole square divided by 15 by root 3 whole square. Once we simplify this, we get 3738.2366 watts. And let us choose current scale 1 centimeter is equal to 1 ampere. And let us calculate the no load current per phase. So that is line current is given in the test data, that is 4.2 amperes. So per phase current we calculate as I naught, that is 4.2 divided by root 3. So that is we get 2.424 amperes. This is the per phase current which is going to be used while drawing the circle diagram. And we have already taken the current scale as 1 centimeter is equal to 1 ampere. So for this, the distance will become 2.424 centimeters. Now, we draw the circle diagram using this data like this. So this is the voltage axis. At 80.5 degrees, we draw the current vector which is called the I naught, represented by O dash like this. And this is the angle phi naught. And then draw a parallel line to the x-axis, that is OX like this. Now we draw the ISC, that is 15 amperes, whose distance will become here 15 centimeters at an angle of 78.85 degrees with respect to the applied voltage, that is phi SC. Draw a line OA with a distance 15 centimeters like this. So this completes the representation of I naught and ISC. Then draw a line meeting O dash and A like this. And this O dash A we call as output line. Now draw a bisector, perpendicular bisector, the output line, that is O dash A, and that perpendicular bisector will cut the O dash B line at point C like this. Now with point C as center, O dash C as radius, draw a semicircle like this, so that it will cut the horizontal line at point B. Now Draw a line from point A dash. Now draw a line from A to the OX, which is parallel to the y-axis, that is voltage axis, like this, and that line will become AD. And measure this distance, and this is going to be used to decide the power scale. When the distance is measured between A and D points, then the distance is coming as 3.55 centimeters. So this is the line which represents the rotor copper loss when the normal voltage or rated voltage is applied to the three-phase induction motor when the rotor is blocked. So now we can decide power scale is equal to WSN by LAD, means distance between A and D. And we know what is WSN, which is calculated already. That value is 3738.2366 watts divided by 3.55 centimeters. So we get 1053.024 watts per centimeter. Now we divide the line AF in the ratio of 1:2 by measuring the distance AF. So from the circle diagram, the distance AF is coming as 3.55 centimeters. Now we have to divide this AF as AE and EF. So EF is taking two parts, whereas the AE taking one part. So the total we can write like this. EF is nothing but 2 times the AE. So now we can calculate what is AE. That is nothing but AF by 3. AF value is known, that is 3.55 centimeters divided by 3 means we get 1.0833 centimeters. So now we can calculate EF, which is 2 times the AE. So that is 2 into 1.0833, that is 2.166 centimeters. So by knowing this AE and EF, we can find out the point called E on this vector on the circle diagram. So from A, measure the distance 1.0833 centimeters so that we get the point called E, and then rest of the distance is nothing but EF, which is nothing but 2.166 centimeters, like this. This bottom part, that is EF, represents the stator copper loss, which is 2 times the rotor copper loss, and rotor copper loss is represented by AE, like this. Now draw a line from E to join the point O dash, like this, and this line represents the torque line. And after this, draw a line A dash, which represents 125% of the full load output of the three-phase induction motor. To draw this, we should calculate what is the output, full load output at 1.25 times or 125%, that is 1.25 into 4.5 kilowatts. 4.5 kilowatts is the full load output which is given in the data. Now we are calculating at 125% what is the output, that is nothing but 125% of 4.5 kilowatts, that is 5.625 kilowatts. And we know what is the power scale. So to decide A dash, so we have to use the power scale, that is 5625 into 10 cube divided by 1053.024 This is the power scale. So then we get A dash as 5.3417 centimeters. So that we represent, so here we draw a line at a distance with a distance called 5.3417 centimeters like this, which is parallel to the y-axis, that is voltage axis, like this. Now draw a parallel line, the output line, like this from A dash, that cuts the semicircle at point P like this, A dash to P like this. So this point P should be connected to the point O by a line like this. And this line OP represents the current corresponding to the new output power, that is 125% of the full load, and we call that as 125% full load current represented by OP, and this will make an angle called phi FL like this with respect to the voltage. Similarly, draw a parallel line to the torque line and tangent to the semicircle like this, which cuts the which touches the semicircle at point J like this. Now from point J, draw a parallel line to the y-axis, that is voltage axis, like this, up to the torque line like this. And this line cut the torque line at point K. Similarly, draw a parallel line from point P to the y-axis, that is voltage axis, so that it will cut the output line at point Q and the torque line at point R, and it will cut the O dash B at point S, and it will cut the OX axis at point T. This PQ represents the output corresponding to the 125% load, and whereas PT represents the input to the motor, and this J represents the maximum torque developed. So when we measure the distance PQ, which represents output, that is nothing but 5.35 centimeters. Similarly, when you measure QR, when we get here 0.3 centimeters. Similarly, when you measure the RS, we get 0.58 centimeters. Similarly, when you measure the distance P and T, between P and T, that is PT, which represents the input as 6.55 centimeters. And when we measure the distance O and P, so that which is nothing but phase current at 125% full load output, that is nothing but 8.85 centimeters. So having known all these distances, now we can calculate what is the line current which is to be required, which is to be calculated for this problem. So for a delta connected system, line current is root 3 times the phase current. From the circle diagram, we get the phase current, which is represented by OP, that is root 3 into L of OP into current scale. So root 3 into L of OP means OP is nothing but 8.85 centimeters, and current scale we know that is 1 centimeter is equal to 1 ampere. So we can calculate line current at 125% of the full load is nothing but 5.3286 amperes. Similarly, when we measure the angle between the applied voltage V and the angle between this phase current called OP, then we get there 41 degrees. So when we calculate the cos of that, then we get to 0.7547 lagging, and which is the second question answer. So similarly, we can calculate what is the efficiency of this motor at 125% of the full load. So that is PQ divided by PT into 100. PQ represents the output, so that is nothing but 5.35 centimeters, and the input is line is measuring as 6.55 centimeters. So because both output and input have the same units, so we use this distances without converting them into power. So multiply with 100, then we get 87.68 percentage. So when we draw the exact diagram with the AutoCAD, then we get the diagram like this. This is voltage axis and this is the OX, and we find this is nothing but stator copper loss, whereas this is the rotor copper loss, and this is output line, this is the torque line, and this OP represents the load current, phase current at 125% of the full load output. Similarly, this P represents the input power at 125% of the full load output, and similarly this PQ represents the input at 125% of the full load output. So let me summarize once. So we have seen that first we identified what are the unknown parameters. They are nothing but line current and the power factor and also efficiency, and then we have seen the given data and then we analyzed it, and from that we got what is phi naught and what is phi SC, and after that we have drawn the circle diagram. From that first we calculated what is the out or the power scale, and similarly we also seen the what is the current scale by assuming 1 centimeter is equal to 1 ampere, and then we also saw how the circle diagram came into existence from the circuit theory, and using that we have drawn the circle diagram for this three-phase induction motor, and from that equivalent the circle diagram, which is nothing but current locus diagram, we found the efficiency of the three-phase induction motor.